So this is going to be the first of 3 videos replacing the lecture for Wednesday, October 9th. The subject of these lectures is going to be relative velocity. This is going to be a standalone topic that will only be covered in these videos. This is going to be a more challenging topic than was covered in the previous videos, so please watch these carefully. And if you have questions, please come in on Wednesday and ask the subs any questions you have. Okay. So to get started, let's say we have 3 people moving in the Cartesian plane, right? Let's say they are person A, person B, and person C. Okay. Now, let's say you were standing next to A and you asked how you could get to the position of person B. Person A might respond by telling you how far and in what direction you would have to go to get to the position of B. In other words, A might give you the displacement vector you would have to follow in order to get from his position to the position of B. So let's draw in that displacement vector. Okay. Let's call this displacement vector RBA, the position of B with respect to A, right? Similarly, if you were standing next to A and asked how you could get to the position of person C, person A might describe a displacement vector you could follow that would take you to the position of C. In other words, A might describe to you position vector RCA, which gives the position, or which gives the displacement of person C with respect to person A. And similarly, we could draw a vector that goes from B to C. And this vector we could call RCB. This is the position of C with respect to B. Okay? So the 3 vectors together, we have the position of B with respect to A, the position of C with respect to B, and then the position of C with respect to A. Okay? Now, one of these vectors is the vector sum of the other 2. Right? So ask yourself which of these vectors is the sum of the other 2, and if you don't see it right away, just pause the video, think it through, and then turn the video back on. Okay. Notice that we can look at position of B with respect to A and position of C with respect to B as if they're being added tip to tail here to give us the position of C with respect to A, right? So thinking about how tip to tail addition works, position of B with respect to A plus position of C with respect to B give us position of C with respect to A. Let's write that. We have position of C with respect to A equals position of C with respect to B plus position of B with respect to A. Okay? Now, let's say we were going to take a time derivative of this. Okay? So just take the time derivative all the way through, and we'd have derivative of RCA with respect to time equals derivative of RCB with respect to time plus derivative of RBA with respect to time. Okay? Right, so we have all these quantities here which are derivatives of position vectors, and the derivative of a position vector is a velocity vector. Okay? So this expression on the left here would be the velocity of C as seen by person A. Right? This would be the velocity of person C as seen by person B. And this would be the velocity of person B as seen by person A. Okay? So what we have here is going to be the basis of all the relative velocity problems we do in the videos and then also on your homework. Okay? So I like to call this the sandwich rule. Okay? I call this the sandwich rule because if you look at this, on the left I have C and A, right? And on the right you have C and A on the outside, and then the B's in the middle, right? So it's like you start with C and A, like the pieces of bread, separate them, and then drop in a couple letter B's. Thus, velocity of C with respect to A equals velocity of C with respect to B plus velocity of B with respect to A. It's like a sandwich with the B's. Okay? All right. Let's look at a simple example of this. Simple example here. Let's say we have a flatbed truck and a road. Okay. So we have a pedestrian. We have a pedestrian standing on the side of the road here. And on the truck, we'll have a jogger. And the jogger is running from the back of the truck towards the front, okay? We'll have the truck driving down the road at 15 meters per second. And we'll have the jogger running from the back of the truck towards the front at 5 meters per second. Right? Now there are three different objects here. We have the truck, which will denote T. We'll have the jogger, who's on the back of the truck here, will denote J. And then we have the pedestrian P. Okay. So as a quick exercise, in using the sandwich rule, see if you can work out the velocity of the truck is seen by the pedestrian. Okay. The velocity of the jogger is seen by the truck, or perhaps the velocity of the jogger is seen by the truck driver, right, who's sitting here and sees the jogger coming towards him, and then see if you can work out the velocity of the jogger as seen by the pedestrian. Okay? We want the velocity of the truck as seen by the pedestrian. The velocity of the jogger is seen by the driver of the truck, and the velocity of the jogger is seen by the pedestrian. So pause the video for a few moments and see if you can fill this out on your own. All right. So here's the solution, right? The truck is driving down the road at 15 meters per second, and the pedestrian is fixed to the road. So the pedestrian would just see the truck going by at 15 meters per second. Right? The jogger is running along the flatbed at 5 meters per second with respect to the truck. So that 5 meters per second is just giving you the velocity of the jogger with respect to the truck. Okay. Now, how would we get the velocity of the jogger with respect to the pedestrian? Now, you might look at this and say, oh, that's so easy, but we'd like to take this as an opportunity to practice using the sandwich rule. Okay? So, here's what we're going to do. Okay. The general principle in the sandwich rule, right? Velocity C with respect to A equals velocity C with respect to B plus velocity B with respect to A, right? The idea is if I have the C and A on one side, I open them up, drop in a couple B's, okay? So anytime we're describing relative velocities where you have three things moving with respect to one another, the addition law for the velocities is going to follow this pattern, okay? Let's see if we can take these three velocities here and make a sandwich rule out of them? Well, here's how we do it. We have velocity of jogger with respect to pedestrian. So I'm going to take the J and the P, and I'm going to open them up and stick in a couple T's to make a sandwich. And then I have velocity of jogger with respect to pedestrian equals velocity of jogger with respect to truck plus velocity of truck with respect to pedestrian. Velocity of jogger with respect to truck was 5 meters per second. Velocity of truck with respect to pedestrian is 15 meters per second. Okay. And you add those together and you get 20 meters per second. Okay, so the velocity of the jogger with respect to the pedestrian is 20 meters per second. Okay. Now, you might say, oh, that's kind of obvious. Maybe you think this is kind of obvious and you could have done it without the sandwich rule. But the point is, this is a simple example which lets us practice the method so we can start to use this in problems which are somewhat harder. Okay? All right. So I'm going to take you through another example now, and this is going to be a conceptual example, no computation, but it's going to be important to understand what I do here before you look at the next video where this is all going to become a computation. Okay? Okay, I just erased the sandwich rule from there. Let me copy it over here for quick reference. All right. Okay, now in the next example, we're going to look at the motion of an airplane through the air with and without the presence of wind. Okay, so if we're looking at the motion of a plane through the air with and without the presence of wind, we're basically looking at three things moving relative to one another. We have air, which will denote A, the plane P, and the ground G. Okay? Now to start, let's say there is no wind. Let's say there is no wind. Now let's have some compass directions here. And let's say the plane wants to fly to the west, which would be leftward on the board according to these compass directions here. So the plane just points itself west. Plane just points itself to the west and pointing itself to the west and then starting to fly. The plane moves westward through the air, and I indicate that the plane is moving westward through the air by saying that the velocity of the plane through the air is a vector pointing westward. If there is no wind, by which I mean that the air is not moving, then the plane would also be seen as moving westward by an observer standing on the ground. Okay? So if there's no wind and the plane points itself west and flies, we have velocity of plane with respect to air is towards the west, and velocity of plane with respect to the ground is towards the west as well. Okay? Now we're going to put in some wind. Wind is motion of the air with respect to the ground, and let's say that that wind is blowing from north to south. Okay, so we have wind blowing from north to south. Wind is motion of air with respect to the ground, so this vector here would be velocity of air with respect to ground. Okay? Now let's say that the airplane again points itself towards the west. Okay, so the airplane is again going to point itself towards the west, and when it starts to fly, it will move westward through the air. So we have velocity of plane with respect to air like so. Okay? Right? Now, if there was no wind and the plane pointed itself to the west, it would simply move west, right? Except now we have wind blowing from north to south, And even though the plane is moving westward through the air is moving to the south, so the plane ends up going like so. Okay? Again, no wind, the plane points itself west and simply moves west. But with wind blowing from north to south, the plane points itself to the west. It is moving westward through the air, but the air is moving towards the south, and the plane ends up doing this. Okay? So suppose now we would try and figure out the velocity of the plane as seen by an observer standing on the ground. How could we do that? Well, we could use the sandwich rule again. Here's what the sandwich rule would look like for this problem. We could say velocity of plane with respect to ground equals, okay, we'll use sandwich rule. This time we're going to take the P and the G, take the P and the G, open them up, drop in a couple of A's, and we got velocity of plane with respect to air plus velocity of air with respect to ground. Okay? So velocity of plane with respect to ground equals velocity of plane with respect to air plus velocity of air with respect to ground. That is the sandwich rule applied to this problem. Okay? So what that's telling us is if we want to find the velocity of the plane with respect to ground, we just do a vector addition of these two guys. Okay, so let's draw out the vector addition. We got velocity of plane with respect to air here, pointing west. Velocity of air with respect to ground here, pointing to the south. So velocity of plane with respect to air pointing west, velocity of air with respect to ground pointing south. And according to the sandwich rule, the velocity of the plane with respect to the ground would be the vector sum right in here. Okay? So then here we have the velocity of the plane with respect to the ground pointing southwest. So in this case, so with the plane pointing itself west and the wind blowing to the south, the airplane ends up moving towards the southwest. Okay? So in the next example we do in the next video, we're going to do a calculation based on essentially that picture.